Hey everyone, welcome to the next video for our course Matter and the Environment. In this video, we will talk about the gas laws, the different gas laws, and basically the procedure or the approach to have in all of these different problems, having so many variables, specifically for ideal gas laws and the combined gas law and the derivatives of all of these gas laws. So important things to consider when we're talking about gas laws are the units that we are going to be handling, the different units of different variables, and to be sure that we have the appropriate numbers or values according to the units that we're handling. So in this video, I will jump ahead into the formulas and the procedures and the problems in order how to solve or approach these type of problems. So let's start with ideal gas law. And the ideal gas law formula is the one that you see right now in the screen. As you can see, there are 5 different variables in here to consider. Each one of them meaning a different thing, and each one of them having different units. The first one, according to the color code, P for pressure, V for volume, and then we have this equal sign. This basically means that we will have the left side of the equation with pressure and volume, and the right side of the equation with N, R, and T. N standing for the number of moles, basically, that we are given or asked to define. R, which stands for the ideal gas constant. This is a fixed number that we will be given, or basically given, that we need to consider for doing all of our operations. And the T in our equation stands for temperature. Remember, every time we use temperature in any of our equations, we have to use the Kelvin scale. Most of the time, we will be given our temperature in Celsius, and or it could be also given in Kelvin, but it's important to consider that if the temperature is given in Celsius, we need to make this conversion from Celsius to Kelvin in order that we can actually use it in our equation. So remember this formula as the ideal gas law formula. So let's see each variable and some specifics about each of these variables. So for the first one, for pressure, basically remember that the units, or more importantly in this case, is the type of units that we will be using, specifically atmospheres represented by ATM in lowercase, kilopascal, which is another unit of pressure, or millimeters of mercury. All of these 3 are different units provided for the variable pressure. So you don't actually have to convert from one to another just to use always the same one. It just needs to keep, to be constant. If we began using atmospheres, then we use atmospheres throughout the problem. If we began with kilopascals, we continue with kilopascals throughout the problem, and so on and so forth. The next variable is volume. Volume, most commonly, we will be using liters as the unit for volume for this type of problems. So again, you don't have to convert from one unit to the other. You just need to be sure which unit you're given for volume and keep the same unit throughout the problem. For moles, remember everything we saw back then in stoichiometry. Moles, this concept is still relevant. So every time we have 1 mole, that would be equal to 6.022 times 10 to the 23rd molecules or atoms or particles, right? So these moles, don't forget about this stuff from stoichiometry. It's actually connected with everything that we will see from here on related to gas. And temperature. Temperature, remember, as I was telling you before, we'll be using Kelvin as our scale. Kelvin is like when we use for temperature a scale that we call Celsius. Um, some countries still use Fahrenheit, but in many scientific calculations, we use the Kelvin scale, right? So how do we change from Celsius to Kelvin scale and back from Kelvin to Celsius, right? Depending on the type of question or the thing that they're demanding, most commonly, the problem will be given a temperature in Celsius because, it's simpler to measure, everyday thermometers or everyday, measuring tools for temperature are very accessible in Celsius specifically. So whatever amount you're given in Celsius, basically you just need to add 273.15 so you can get the temperature in Kelvin, right? This 273.15 is the unit or the measurement that we can consider the standard temperature for these problems, right? Whatever amount of Kelvin that you may have, then you just basically subtract 273.15 so you can get the temperature in Celsius, right? So basically, if you're going from Celsius to Kelvin, you add, and if you're going from Kelvin to Celsius, you subtract what we call the standard temperature, which is 273.15. Speaking of the constant, this ideal gas constant that is represented by the letter R, we can have different values. Now, this will depend basically of what we have in pressure, the unit of pressure. So if we are given, for example, 1 atmosphere unit for pressure, then the constant R for R that we will be using is going to be the one that includes the unit of atmosphere within its unit, right? So in this example, for 1 atmosphere, we will be using this number that we have in the left, right? Consider that this number is the one that you will be using in your calculations. And this whole thing that you have next to it is what we call the unit. This would be the unit assigned to this particular constant. Now, in your procedure, you'll need to substitute these units with a value. They're just a unit, right? Just as ATM or atmosphere is the unit for pressure, or 298 Kelvin would be the unit for this number for temperature. This whole thing that we have in here, all of this represents the unit for our R. So you can include all of these units in your procedure or leave it out to the end. Either way is fine, but I'll show you one of the advantages of actually including the whole thing into your procedure so you can keep track of the units that are getting canceled and the final unit that your answer is going to be. On the contrary, if your pressure is not expressed by atmospheres, but instead is expressed by kPa, which is kilopascals, let's say we have 20 kilopascal as your unit of pressure, then this unit of pressure will condition that we will be using this number instead, right? The one in the right. So instead of using 0.082, you will be using 8.31 for that particular problem, right? So in summary, your R depends on whatever unit you have in pressure, right? We'll practice this in a second. So these concepts of standard temperature and pressure is basically something that is very common also in type of problems to be expressed. If you have a problem that says, this volume at standard temperature, then we would mean this ST, right? The standard temperature, which will be 273.15 Kelvin. This number, which is the conversion factor that we use to change from Celsius to Kelvin, is the one that you will be using every time a standard temperature is mentioned in any problem, right? Likewise, if you're given standard, let me put in like standard pressure, then the pressure that you will be using is 1 atmospheres, right? Or 1 ATM. Especially if you're not given any unit for pressure, always go with ATM, right? With atmospheres. Unless you're being specified per kilopascal or millimeters of mercury, then you use that. But if you're not being specified and you are given SP, like standard pressure, you can use this number 1 for atmospheric units. So essentially, the way that we identify these type of problems, or that we have to approach this problem using the ideal gas law formula, is that we're being given these variables, right? We're given a pressure, we're given a volume, we're given a temperature, or given moles, right? Additionally, we're also being specified about the value of R. Remember, there will always be one of the variables that is not given. So let me write down the formula, like PV equals nRT, right? Consider this. R is a constant, right? So this probably will be already expressed in some sort of way, not included in the problem, right? And besides R, you will be having 4 variables, right? Now, from these 4 variables, you will be given 3, and one of them, let's say temperature, right? One of them is going to be your question, right? So the question directly would be using one of the words for questions, like what is the temperature, or how much is the measurement of temperature, or something like that, right? So the other 3, you would probably will be given or provided clues or hints about what is it, right? For pressure, remember, it could be at standard pressure, or basically given a number for pressure, right? Same for the others. So the way that we're going to approach this is first identify the variables that you're being given, and then substitute it in the equation, and then you solve for x. So let's do some sample problems using this ideal gas formula, right? So in this first problem, we are given this this problem that says if a 3.0 liter tank of oxygen contains 0.45 moles of oxygen at 24 degrees Celsius, what is the pressure in atmospheres in the tank? So again, looking at the formula, we're being given here liters, right? Which stands for volume. We are also given information about moles, right? So we got this down. We're also given information about temperature, although it's not in Kelvin, so we need to change this, right? So we are going to be using the standard temperature, which is 273.15 Kelvin, plus our value for Celsius, right? So now we just add this number and we get 297.15 Kelvin. Now that we have our value in Kelvin, we got this variable down, right? R is being specified by our problem, so we also got this down. So our X in our equation is going to be pressure, which kind of makes sense, right? So we can now substitute. So we can have our X multiplied. Remember, when you have all of these variables sticking together, like no spaces in there or no any other sign, that's a multiplication. So our pressure is going to be our X multiplied by our volume, which is 3.0 liters, equal to our moles, which is 0.45. Include the unit there so you don't get lost. Our R, which is 0.0821. And the whole unit for this would be liters times atmospheres divided by mole times Kelvin, right? Just do the parentheses here larger so we can include the whole thing. And our temperature, which was previously calculated to 97.15 K, right? Kelvin. So now what do we do? Well, now we solve for X. How do we solve in this case? Remember, this guy is multiplying here. So it's actually going to cross over dividing, right? So we can actually just move this 3.0 L down here, because remember all of this is dividing. So we will get 3.0 liters, right? So let me just rewrite this as a parenthesis times liters, so we can get all of these units here. So let's have this here as an X. Now, the reason I just put this number down here with these units that were down here originally is because this whole thing at the end is dividing, right? So this sign that we have here is already giving us this form of a fraction. So this is kind of helpful also to keep track of our units, because look at what's happening next. Now, because we have liters on the top, we can get rid of those. We have moles on the top and in the bottom, and we can get rid of those units. And we also have Kelvin on the top and in the bottom. Which unit is going to be remaining in there? Atmospheres, right? Now, which unit are they asking us for? Atmospheres. So far it makes sense, right? Now, what's the other thing that we have left? Only the numbers, right? So we can rewrite this as x equals 0.45 times 0.0821 times 297.15, and then all of this is divided by 3.0, which is the same as 3, right? And all of this at the end will have a unit of atmosphere, right? So once you finish doing the whole calculation, the multiplication and the division, at the end, you should be having your final answer as 3.65 atmospheres, right? This is the final answer for our pressure specified in atmospheres, right? Now, remember, be careful when you're setting this up in your calculator. I recommend you do the whole thing in once, right? Especially if your calculator is a scientific calculator, by using correctly the parentheses, right? Be careful here. Well, in this case, it's not really that different because everything is multiplying and then dividing, but you want to be extra sure that in your calculator, you have the whole thing, especially when you have other type of you know, processes going on, that you first do the whole thing and then divide everything by 3, right? Many mistakes, not in this case, but many mistakes are done because setting up additions and multiplications, all of this, without actually using the parentheses to provide the calculator a stronger sense of the order of operations, right? Especially if you're setting this operation for the temperature also in there, right? Some students like to do the whole thing like 0.45 multiplied by 0.082 multiplied by the number that is given in the problem for Celsius plus 297.15, all divided by 3, right? This, in theory, is fine. It would be giving you the same answer. The problem is if you fail to put like correct parentheses in the whole thing, this addition that you have here is going to be, cutting your problem in two halves, right? Because it's going to be making the multiplication of this section first, the division of these two guys first, and then adding the results of both. So it's going to get messy. So I do recommend be careful with that and give it a try several times just to be sure that you're making the process correctly in your calculator. All right, let's do the second problem. In here, we have also information. Check it out. Ball is filled 2.1 moles of gas. Temperature is 25 degrees Celsius, and the pressure is 2.5 kilopascals, right? How do I know this is the pressure? Well, number one, the problem is telling you, right? The pressure in the ball is. The second part is the unit, kilopascal, is for pressure, right? So notice how our R changed. Instead of being 0.0821 as we had before, now it's 8.31. This is because of the unit of pressure that we're using. Our R changes, right? So what's the problem asking us to get? The volume, right? So this guy is going to be our question. So let's start by using the formula and substituting the values, right? So for pressure, we got 2.5 kilopascal multiplied by B, right? Which is our X equals to our moles, which is 2.1 mole, times our R, which is over here, 8.31, and then we got here liters, kilopascal, all of this over Kelvin times mole. And then we have our last value, which is the temperature. So it's going to be this 25 plus the standard temperature, right? So 25, we get 0.15 in here. We got 8, 9, and 2. So we got 298.15 K, right? So we can actually extend this to make the whole thing into a fraction. And notice how to solve for X in here, we're going to do the same problem as before, right? The same process as before. We're going to put this down here. So we're going to put 2.5 kilopascal times all of these other units. And now we can erase it from here. All right. So now notice that we have repeated units, right? Mole can go out, kilopascal can go out, Kelvin can go out, and we're just remaining with liters. This can be, helpful to double check if we're doing everything correctly. It makes sense, right? For volume. Okay, so now we do the whole calculation, right? We can do our process just by doing 2.1 multiplied by 8.31 multiplied by 298.15, right? Over 2.5 is as the denominator, right? All of this at the end, you will have the unit of liters here, right? So at the end, your answer should be 2081.21 liters, right? Again, careful with the parentheses, the order of operations, be sure that you're setting this up correctly. Now for the third problem, in here we're going to be solving for moles. The subtitle tells you which process are we going to do here, all right? So let's analyze. A gas tank has a volume of 130 liters. How many moles are required to fill the drum at 110 kilopascals at a pressure of 27, right? So let's substitute our formula. For pressure, what do we got? 110, right? Kilopascals. For volume, we got 130 liters equals to our moles, which is going to be our question, right? We can set up the X in here. For our constant, we're given according to the pressure, remember, kPa, kilopascal, 8.31, and we can include the whole units here, liter, kilopascal, all of this over Kelvin times mole, right? And our temperature was 27, right? So it's going to be standard temperature plus 27, right? This is going to give us in here to the 315, right? 15 Kelvin, right? So what are we going to do now, right? Notice how our X now is on this side, right? So the thing or the process and how we can solve this more efficiently is let's look at the formula, right? Like here in the top, these two guys that are multiplying these N or moles, we can send them over to the other side, dividing, right? That way you leave moles alone and we can solve for moles, right? So let's do that. But notice what's going to happen. So we're going to take all of this. Let's put it in here. We're going to use this to divide only, only R and T, right? So it's going to be 8.31 liters times kPa, right? Times 315 K, right? And this denominator that was in this fraction is also going to be sent down here, right? So we're going to have K or Kelvin times the mole, right? So let me erase all of this from this side. And we're done, right? Now we solve for X, which is for our moles. Now notice in here, we have a double fraction, right? In the denominator. Well, it's not a double fraction. We have a fraction as the denominator. So we need to remember one thing, that this whole thing on the top, on the numerator, we can also express this as a fraction, right? So it's going to be 110 kPa multiplied, which is pressure, times the volume, which is 130 liters, right? And all of this divided by 1. This way, we have one fraction in the numerator and one in the denominator. If you remember from math, what happens now is the ones on the outermost side are going to be joined together in the numerator. And the ones that are closer together are going to be joined now in the denominator. Right? So we can also express this as 110, as 110 kPa times 130 liters, right? Times Kelvin times mole, ran out of space in there. All of this divided by 8.31 liters times kPa times 300.15 K, right? All of this would be equal to X. Now we just cancel the units that are redundant, right? Or that we have on the top and in the bottom. Kelvin can go out and we're just remaining with the mole in there. We can rewrite this to see it cleaner as 110 times 130 mole over 8.31 times 300.15, right? Now we can do the math, and as our final answer, we will get 5.73 moles, right? 5.73 moles of what? Of the gas, right? We're not being specified in here which gas, so you can just leave it like that. 5.73 moles would be your final answer for this process. Now, of course, as you get used and familiar with this process, you can, let's say skip steps. It's not the correct term, but you can move faster through the procedure so you can get to the final answer, right? Again, if you decide not to use the units, that's fine, that's your choice. At the end, you should get the same number. Just don't forget the unit that we're talking about, right? Which is moles. This is basically the complete long explanation and how we got there. For the last example, we can solve for temperature. So in here, let's check the problem. We have a 5.0 liter tank of carbon dioxide gas, which contains 7 moles of carbon dioxide at 4.8 atmospheres of pressure. The question is, what is the temperature in Kelvin in the tank? So we can substitute our values for pressure, which is 4.8 atmospheres. Notice here we're using atmospheres again. 5.0 liter, right, equals to 7.0 mole. Our constant, which is 0.0821. Let me just skip the units and I'll just put them at the end. And the temperature is our question, right? So in here, we need to solve for this guy. Just as before for moles, we can take this unit and send it divided here in the bottom, right? So let's do that. So we are gonna take here the 7.0 mole and the constant, right? 0.0821. And all of this will be equal to our X, right? Once again, once you do the whole equation, the whole process, you will get as an answer 41.81. And this number, if you follow along the whole units, as I showed you before, at the end, the unit that is going to be left over is going to be Kelvin. For this reason, this is your final answer, right? Because the question is asking for the temperature in Kelvin. Now, let's assume that our question, our problem, was asking for the temperature in Celsius, right? So the next step, once we find out the temperature in Kelvin, this is not going to be our final answer. To this, now we need to subtract 273.15. Remember, this is our standard temperature. So we can get our answer in Celsius, right? Now, again, this step is only necessary if the problem is asking you for Celsius. If it's asking you for Kelvin, then the final answer would be 41.81. All right, so that's essentially for the first part, which involves the ideal gas law. Now, for the second part of this whole topic, we're going to talk about three different laws, and at the end, one joint combined law, which is actually called like that, and which will have a relationship between two or three variables specifically, right? For the first one, which is called the Boyle's law, in here in Boyle's law, just as you see on the screen, there's a relationship between two variables, pressure and volume, right? We have pressure on one side and volume on the other one. So the relationship between these two variables will be basically an inverse relationship in the sense that if one variable actually increases, like in this case, the volume going to the right starts to increase, the pressure, notice how starts to decrease, right? So this is what we call an inverse relationship. And this Boyle's law, we can also represent it in the lab, which you actually experienced it a couple of weeks ago by using the syringe with the marshmallow inside of it, right? So as you increase the pressure exerted in that example of the syringe, you would push with your finger, then you increase the pressure applied in each scenario and the volume started to become lower, right? So the marshmallow started to shrink as you increase the pressure, right? So this is a very good example on how to represent this Boyle's law. This Boyle's law is actually represented by the formula that you see right now in the screen. Noticing here we have the same units of pressure on both sides and volume on both sides. What is the difference? They have a number here, right? This number represents the initial and the final pressure. So we're talking about a change in here, right? There was an original pressure and there was a change pressure, right? Or a final pressure. And same with the volume. So if we consider that the pressure increases in here, like in two scenarios, then the volume would have to be decreasing, right? According to our experiment. So in this type of problems, the temperature that we like as an additional factor would be expressed to be constant or not changing. Because what we really want to see here is the relationship between pressure and volume in two different stages, right? Like an initial and a final. So every time you see here initial pressure or original pressure or the pressure that it was before or some sort of identifier that tells you that it was basically initial, this is going to be represented by a P1. And the final pressure or the pressure after in the day after or something like that, that would be P2. Same rules applies for volume, for initial and final volume, right? So we would have normally in these type of problems, at least 3 out of these 4 variables, speaking of initial and final things, right? And temperature can be expressed as constant. They can give you a number, but they would say like, that's like there was no change or, the temperature, it was always the same, or might not even mention temperature, right? So this would give you the hint that we're talking about a Boyle's law problem. Let's see one example. So in here it says a balloon with helium gas has a volume of 400 milliliters at 2.5 atmospheres. Noticing here we have volume and we have pressure, right? If the volume expands, the verbs in here, the context of the text question is very important. This is going to give you the hint or the answer basically on which one is the initial and which one is the final, right? So it says the volume expands to 850 milliliters at a constant temperature. What is the new pressure, right? So this new pressure is highly suggesting that this is going to be P2, right? So this has to be V2. Therefore, these are V1 and P1, right? So now let's substitute this in our original formula, which we have up here, right? So P1 is 2.5 atmospheres, right? Multiplied by our volume 1, which is 400 milliliters, right? Equals to the pressure 2, which we don't know, which is X, and volume 2, which is 850 milliliters, right? We can solve for X by sending this guy over here, and we can put this out, right? And this is going to be our formula to getting our new pressure, right? Or P2. After this, we can do the math and we will get as a final answer 1.18 watt. So check out the units. We got milliliter, milliliter. So we're going to be left over with the atmospheres, right? So this will be our final answer for P2, right? So this is going to be our new pressure according to this problem. Now let's see for problem 2. It says a sample of gas has a volume of 35 liters at a pressure of 500 millimeters of mercury. Notice that this, you can go back and check, this is a unit of pressure too. The question is, what is the volume of the gas in liters at 1,200 millimeters of mercury if there is no change in temperature, right? Okay, so whatever we have here, a sample of gas has, so this is basically like the statement, right? We have this, so this is for volume 1 and this is for pressure 1. It says, what is the volume at 1,200? So this is going to be our pressure 2, right? And the question is, what is B2, right? So let's put this in our formula. So we have 35.0 liters, right? Our pressure 1 was 500 millimeters of mercury equals to pressure 2 is 1,200 millimeters of mercury multiplied by V2. So that's our question, right? So we can solve for X by sending the 1,200 millimeters of mercury down here. Oops. There we go. And we can get this rid of here. And this is going to be the X, right? So after doing the math, we will have 14.58 liters, right? How do we get liters? Be sure to cancel out the units that are repeated on the denominator and the numerator. So at the end, our final answer would be this for the volume 2, right? All right, so let's continue now with Charles' law. Charles' law also follows a relationship between two variables, but instead of being pressure and volume, in here in Charles' law, we will talk about the relationship between volume and temperature. As you can see here in the graphic, temperature and volume follow this linear proportional line, right? As in the sense that when temperature increases, volume also increases, right? This means they have a direct relationship and that it's also proportional. So this was represented in the lab by the experiment of having the flask with water and tying up a balloon on top of it, right? So you put this flask in the hot plate. As a hot plate started to increase the heat within the water in the flask, then the balloon suddenly started to expand, right? Because as temperature increases, in this example, it doubled, the volume also increased within the container, right? Notice how in here we're also included the unit for atmospheres, meaning pressure, right? But notice that there is no change. So the atmospheric pressure, in this case, did not play a role in this relationship between variables. So we can basically ignore it, right? And focus only on the changes between volume and temperature. So Charles' law is basically represented by this formula that you see on screen. Notice how Boyle's law was a multiplication between pressure and volume, but in here is going to be a division, a fraction, a ratio between volume and temperature, right? So same as before, we will have an initial volume and a final volume represented by 1 and 2. And we will have an initial temperature and a final temperature represented by 1 and 2 respectively. In this sense, pressure remains constant, or is just telling you atmospheric pressure, or is just telling you a number and saying that the conditions remained after an X amount of time, or something that indicates that it didn't change, right? And similar as before, you will have an initial and a final volume, right? And a final and an initial temperature. So let's see an example of this. In this first problem, we have a soccer ball has a volume of 2.7 liters of air and is inflated to 1.2 atmospheres before the game at a temperature of 20 degrees Celsius. During the game, the temperature increased to 30 degrees Celsius, right? What is the volume in liters? This is our question, right? Of the ball at the end of the game if the pressure remains constant. So by including this statement, we can get rid of pressure, right? We can just focus on the volume that we have in here and in here, and the temperatures that we have here and in here, right? Now, be careful. Not always the smaller number is going to be the initial. We need to be sure of what they're asking us or what they're telling us, right? So in here, the context of the problem helps because it's before the game and then it increased, right, during the game. So we will have our initial temperatures, right? Our initial temperature to be 20 degrees Celsius and the final to be 30. Careful. In here, these guys are in Celsius, right? We shall not use Celsius any time during our equations. So we need to change these guys into Kelvin, right? So we add 273.15 to each of these amounts, right? So 20 degrees Celsius is 293.15 Kelvin, right? And 30 degrees would be 303.15 Kelvin, right? So this is going to be temperature 1, and this is going to be temperature 2. So now we can set them up. So 93.15 and 300.15. If you do this in Celsius, the number is going to be significantly different. So be sure that you use Kelvin always, right? If you're setting up a number in Celsius anywhere in any formula during this type of problems, you're doing it wrong since the beginning. So be sure to always have these numbers in Kelvin. Likewise, the answer within this fraction or this equation will always be in Kelvin. If you're being asked for Celsius, you need to subtract the final answer. All right, so volume 1 was 2.7, right? 2.7 liters at the beginning. Let's put the units here. And the question is, what's the final volume, right? So in order to solve for x in here, we can put this number, this 300, we can send it up, right? Because it's being divided in here, we're going to send it up so it can be multiplied by the 2.7, right? So it's 300.15K, right? And we can erase this whole thing, and this will be equal to my x. Once you do the math, you will get 2.79, and which unit? Liters, right? This would be our volume 2, or our final volume, right? So our final answer would be this guy. One thing, if you did the whole thing with Celsius, your answer is going to be around 4.05 or something, which is significantly different from this, right? So always be sure to use Kelvin within your process. All right, second problem. So we have a gas cylinder containing 25 liters of air during the day at 28 degrees Celsius. At night, it only holds 21 liters. What is the temperature in Kelvin at night if the pressure remains constant? So no pressure in here, so we're gonna get our formula from Charles' law, right? So we're gonna start with the initial volume, which was 25.0 liters, right? And at night, it changed to 21 liters. It's telling you that during the day, it was 28 degrees. So that's 273.15 plus 28. You would get here. So 301, right? So you would get 301.15 Kelvin. So the question is, what is the temperature in Kelvin at night, right? So just be sure to have the number in Kelvin. Now you can solve for x, right? Now, one common problem in here is how to solve for this guy, right? It's not just sending the number in the denominator, in the numerator, all to the other side, but we need to be sure to follow the correct algebraic rules to solve for this, right? So first, we're going to be sending this number. Well, probably your math teacher is going to hate me because I'm oversimplifying this, but we're going to send this number to the top. So we're going to put 3.115K, right? So now we get rid of this number. Now that you have this, what you need to do is just switch these two guys from place. So now you will get x equals 212, wait, that's 21 liters, right? Careful with this. So 21 liters multiplied by 301.15 Kelvin over 25 liters, right? This is the way to, in a summarized way, to solve it, to solve for x. So we cancel the liters and we will be remaining only with Kelvin. After you do the math, you will get 252.97 Kelvin. Notice that the unit that is left over is Kelvin. So this is going to be our final temperature, right? Now, again, this question is asking for the temperature in Kelvin. So this number, because the unit that is being left over is Kelvin, we're fine, we're done. But if the question asks for Celsius, then you would need to subtract the 273.15, which is our standard unit for temperature, so we can get the temperature in Celsius. In this case, we don't need to do that, so we're done. The third one that we're going to study is called Gay-Lussac's law. Similar to the other two, we have a relationship between two variables. In this case, now it's the other two, pressure and temperature, right? So notice how we also have a proportional and direct relationship between the two of them, in the sense that as temperature increases, pressure also increases. This, we saw it in the lab, represented by the hot plate, or the, well, it was actually fire. You had fire and you were heating up a can, right? So the way that the fire heated up the can gradually increased the pressure that it was found within the can. Once you put the can in the cold water, the sudden temperature change actually created this kind of like collapsing or implosion, we can say, where the pressure in the outside was actually larger than the pressure inside of the can, creating this crushing result that you saw in the lab, right? This is expressed by the formula that you see in the screen. Similarly, we have an initial and a final pressure divided by the temperature's initial and final stage. Similar to the other ones, volume remains constant, or the number, basically they give you a number and it's just like there was no change in that. And we have an initial pressure, a final pressure, an initial temperature, and a final temperature, right? Let's see some sample problems. We have a gas has a pressure of 121 atmospheres at 34 degrees Celsius. What is the pressure in atmospheres at standard temperature if there was no change in volume? So it's giving us the original statement, 121 atmospheres over 34 degrees Celsius. So we need to add this to 273.15 plus 34, right? So we can do this, 7 and 3. So we get the temperature to be 207.15 Kelvin, right? At this point, this guy is Kelvin. Equals to the next, the new pressure, which is going to be our X, over the standard temperature. Again, attention here. Standard temperature is this number that we keep adding to everything. So this is going to be 273.15 Kelvin, right? Now we solve for X. So we would have 121 multiplied by 273.15 over 307.15 equals to our new pressure. You do the math and the answer would be 1.08. We take out kelvins and the pressure unit is left over. So this is going to be our final pressure, our final answer also, right? Second problem. It says if nitrogen gas is in a closed container, every time we have this closed container thing, it also means the same as a constant volume, right? Because it doesn't change. It is pressurized. So you put more pressure. Check it out. From 7 atmospheres to 12.5 atmospheres. That means that these numbers are going to be my initial and my final, right? This verb pressurized indicates that there was a change from this point to that point. So prepositions also mark which one is initial and the final. And its original temperature, so temperature 1 was 22 degrees Celsius. So we put 273.15 plus 22. So you get the 0.15, 5, 9, and 2. So we get 295.15 Kelvin. What would be the final temperature in Kelvin? So temperature 2, right, of the gas. So again, to solve for this, we send this guy up and then we switch these two guys, right? So we're going to have 12.5 atmospheres, 295.15 Kelvin, and 7.0 atmospheres, right? We cancel the units of atmospheres. And after you do the math, you get 527.05. And the unit is Kelvin. This will be our final temperature and also our final answer because the final temperature is being requested in Kelvin. So we don't subtract, right? Now, the final stage of all of this We have Boyle's, Charles, and Gay-Lussac's law. All three of these laws can actually join into one combined gas law, which is actually more convenient if you actually first learn this, and then depending on the context of the problem, you just eliminate variables. Because look at this combined gas law. What it actually has is the three variables. So if we agree that the temperature is constant, we can eliminate the temperature and you get Boyle's law, right? If we agree that the one that you're removing is the pressure and the pressure is being constant, then the one that you have is Charles' law. And if we agree that the one that you're removing because it's constant is the volume, then we have Gay-Lussac's law, right? So basically by getting out these variables, either because they're constant or because they're not even regarded in the problem, we can actually, from the combined gas law, we can get the other three laws that we just studied. So here you can see how the combined gas law actually takes from all three of them. See how the temperature is always in the denominator and pressure and volume is always in the numerator, right? If there is no temperature, then basically you have a flat equation, right? There's no fractions in there, just a multiplication. So in these cases, you will have values for pressure, volume, and temperature. Same with initial and final. Initial and final, initial and final, right? Only one of them will not be given, right? That would be the question. In these cases also, there will be no moles included in your problem and no R, right? So this pushes you to think into this is a combined gas law instead of an ideal gas law. Remember, ideal gas law would be an RT. So we have no moles, no R, so we're just left with the other three variables and we get the combined gas law. Additionally, there's, the initial and final aspect of all of these variables. So this is also a hint towards that we're using the combined gas law. So let's see some examples. A sample of 322 liters of hydrogen occupies a volume of 197 at STP, that's standard temperature and pressure. If the initial temperature was 37 degrees Celsius, what's the initial pressure? So our initial pressure is going to be our question. And somehow in the rest of the problem, we should have information for everything else. So let's see. A sample of 322 liters, right, occupies a volume of 197 STP, right? So that's standard temperature and pressure. That means standard temperature, standard pressure is 1 atmosphere unit, right? So if the initial temperature, so this is telling us that the initial temperature has to be this, right? It cannot be the standard temperature, was 37 degrees Celsius. So that's 273.15 plus 37, right? So we get here 11 and 310, right? So our initial temperature was 310.15 Kelvin. What is the initial pressure? So our question is this, right? So now that we have all of our variables, now we just solve for X. So how do we solve in this case? This goes up here and this goes down here, right? So we will get X equals 1, which is the standard pressure, times 197 liters times 310.15, Kelvin over 322 liters times 273.15 Kelvin, right? Once we do the math, we will get 0.69 and the remaining unit will be the atmospheres, right? That belongs to this guy. I didn't write it here, but let's write it here. times atmosphere. So our unit for this would be the 6.69 atmosphere units. This would be for our initial pressure. And the last problem. So we have a sample of gas at a volume of 12 liters at a pressure of 3.2 atmospheres and a temperature of 10 degrees Celsius. It says, what is the volume of the gas under STP? So we have an initial sample of pressure 3.2 atmospheres, right? Multiplied by 12 liters over, so this 10 is 273.15 plus 10, 283.15, right? So 283.15 Kelvin equals to what? That's final pressure, final volume divided by final temperature. So it says, what is the volume of the gas under STP? So the second volume is going to be our question, right? STP means 1 atmosphere unit multiplied by X, which is our final volume, the one that we don't have. And the standard temperature is 273.15 K, right? We solve for X, 3.2, 12, 273.15. And then let's put all of our units, atmospheres, liters, Kelvin. All of this over 283.15 times 1 times units, Kelvin, atmospheres, right? All of this is going to be giving us our X. Units out, Kelvin and atmospheres. So after you do the math, you will get the 37.04 liters, right? Because that's the unit that we were left over with, which this is going to be our volume, our final volume, right? All right. So hopefully that was helpful for you to organize all of the ideas, all of these details for temperatures, for Rs, for atmospheres, kilopascals. And yeah, now you get to practice. And if you have problems with the decimals, it's very common. Don't get frustrated. In most cases, there's a range of accepted answers, so don't get too worried about that. If you get very near to the answer, that means that you're doing things well. If you're very far away from the answer, it's probably because you're missing 1 or 2 steps. Most commonly, the changing from Celsius to Kelvin, right? Or Kelvin to Celsius as a final answer. So be sure to check what is it always at the beginning and at the end. Once you finish the whole procedure, what was the original question? Just to be sure that your final number is actually making sense to the original question. All right. So that's it for now, and I'll see you in the next topic. Goodbye.